Hi there, this is Caroline Wu in Dr. Greco's 10 a.m. Physics 1 class. This is the Test 3 wrapper, and this is problem 2. I actually did not lose the most points on this one, however, it did take me the most amount of time, and it took me way too long to figure these out, and some of them I still didn't get. So let's just start with part A. Two electrons are starting at rest, meaning that somebody is essentially holding these two electrons apart so they have zero initial kinetic energy. So as you can see, the red line, it starts at 0, right? They're initially not moving, and as the electrons are released, they're gonna go away from each other. Okay, so the farther away they go, the less potential energy they have, because the less impact, the less electronic pull they have on each other, electromagnetic forces they have on each other. So as we can see here, they start at a kinetic energy of 0, and they start at the maximum amount of potential energy, because you hold two electrons very close to each other, they're going to repel each other quite a lot. And these two graphs, if you add them together, they're going to equal a total of the total energy that you just sum up, essentially the area under these graphs. And the reason, this was what I couldn't figure out, the reason they start, like the graph starts here and not say like here, is actually just personal preference. Because they start distance r apart, depending on where you put r is where the kinetic energy is 0, and then they're released. If I decide to draw a dotted line here and say here is distance equals r, big R, then I could essentially have my graph going like that. Alright, so the second scenario is when a comet moves away from the sun and it has enough velocity for it to essentially surmount the sun's gravitational pull, so it can essentially escape, right? It has a minimum escape speed, and it doesn't just barely escape. It also has a non-zero speed, as in, you know, it's not perfectly, the energy total is not perfectly on this line. If the purple line was this x-axis line, then the comet would just escape, but it would not have any velocity far away from the sun. In this example, the purple line is drawn above the x-axis line because the comet is still moving. It still has speed when it's very, very far away. So that leaves it a little bit easier for us. That's something that we need to know. And here's kinetic energy, again, going down, potential energy going up. And why would this be the case, right? Why would the potential energy go this way and the kinetic this way? Why doesn't the kinetic energy fall down here? If I hadn't labeled it, would this be the potential or would this be the kinetic? Well, you know that kinetic energy cannot be negative, right? The potential energy, however, can be negative, as you can have negative g m1 m2 over r. That can be actually a negative potential energy, but it can kinetic, there's no. Here, if I just write the simplified version of kinetic energy of 1/2 mv squared, sorry for the handwriting, 1/2 is already positive, mass is going to be positive, and whatever the velocity is, right, it's going to be squared, so the direction of the velocity is essentially canceled out. You can't have the kinetic line as this green line. Alright, so in this last scenario, you have a spacecraft that leaves Mars with an initial velocity that is below the escape speed. So what happens to an object that escapes below the escape speed? It essentially orbits Mars, right? Because it does not have enough energy to surmount and to leave essentially the gravitational pull of Mars. So between r equals rm and r equals r max, what is rm? Rm is essentially the radius of Mars. So if I have this is Mars, this spacecraft is essentially just circling and circling in an orbit around it, right? It can't leave, it can't go like that and just pop off. So essentially we have our energy total here, our kinetic energy as a positive to match, and the potential energy drawn so that when the kinetic and the potential are added together, you get this purple line right here.